For the longest time, we pictured satellites as these lonely travelers, right? Just single dots in the sky, each doing its own thing. Well, that picture is completely out of date. We're now launching entire swarms, basically fleets of spacecraft that have to work together. And that brings up a really fascinating problem. How do you conduct an orchestra of satellites all moving at about 28,000 kilometers an hour?
And when I say orchestra, I'm not kidding. This isn't just about making sure they don't bump into each other. We're talking about getting them to fly in a formation so precise, the accuracy needs to be within a single millimeter. Think about that for a second. A millimeter, while hurtling through the vacuum of space. I mean, how on earth do you even begin to do that?
So here's how we're going to break down this incredible story. We'll kick things off with the big idea that started it all, the virtual satellite. Then we'll get into the unexpected problem that success created, a sky just packed with signals. After that, we'll look at the really clever solution, figuring out how to pick the perfect team. And we'll wrap up by looking at what this all leads to, basically a brand new network built among the stars.
All right, let's jump into part one, the dream of the virtual satellite. The core idea here was, well, it was both simple and totally audacious. What if, instead of building one enormous, ridiculously expensive satellite, you could get a bunch of smaller, cheaper ones to work together, to act like a single giant instrument up in orbit? And that's the whole concept behind what we call formation flying. It's like you're taking a bunch of small cameras and arranging them in a perfect pattern so that when you stitch their pictures together, you get a result that's as good as one giant high-powered camera. You're creating this virtual lens in space that's bigger and more powerful than anything you could ever physically launch. And the physics here is just, it's wild. It turns out the power of what you can see, the resolution, isn't about how big each individual satellite is. Nope. It's about how far apart they are from each other. This means you can spread these things out and simulate a telescope or a radar dish that's the size of a stadium, or heck, even the size of a small city, all without building something that big. But here's the catch. To make that work, to get that perfectly clear, stitched-together image, the level of precision you need is, well, it's just insane. For some of these advanced missions, we're talking about knowing where every single satellite is in relation to the others, down to 1 millimeter. That's not just an engineering challenge. That's a whole mountain to climb. So, how in the world did they pull that off? Well, they came up with a pretty smart leader-follower system. You've got one satellite that's the boss, the cluster manager. It's the brains of the whole outfit. It takes the commands from the ground and then directs the whole team, using these really cool orbital tricks to make sure the entire group moves and acts like one single, cohesive unit. Okay, so this whole idea was a huge success. Maybe a little too successful because it opened the floodgates for launching tons of satellites. And that created a brand new headache. We solved the problem of control, only to be faced with a new one, a sky that was suddenly screaming with signals.
I mean, just look at the difference. Back then, you were dealing with a small, hand-picked team all working together on one mission. Now you have these mega constellations, things like Starlink, that are just flooding low Earth orbit with thousands upon thousands of individual satellites. Every single one of them is a potential signal source. And this isn't some far-off theoretical problem. Right now, if you're in the mid-latitudes, a receiver can look up and see more than 40 Starlink satellites at any given time. 40. That's not a quiet sky. That's a constant buzz of data flying overhead. And here's the kicker. Our hardware just can't keep up. The receivers we have simply can't listen and crunch the data from all those signals at the same time. It's a total bottleneck. So the whole game has changed. It's not about the robotics of formation anymore. It's about information theory. It's about making a choice. Out of all that noise, who do you actually listen to? And that brings us to the really clever part, the modern fix. If you can't listen to everyone, you've got to be a genius at picking who to listen to. You need a super smart algorithm that can scan that crowded sky and say, okay, you, and you. You're my team. Okay, the secret sauce here is a metric with a pretty intense name. DGDOP. Yeah, that's Doppler Geometric Dilution of Precision. I know, it's a mouthful, but forget the name for a second. Think of it like a quality score. It looks at any group of satellites, checks out their geometry, where they are in relation to you, and gives them a score on how good that formation is for getting a super accurate position. And with DGDOP, just remember, a lower score is a better score. So how does it find that low score? There's this awesome method called FCSDP. Think of it like a sports draft. First, the algorithm looks at every single satellite it can see and calculates its unique geometric skill. Step 2, it groups them into teams based on those similar skills. And then, the final step, the algorithm, acting like a coach, picks the one star player from each of those teams to form the absolute best starting lineup.
And does it work? Oh, yeah. Just look at this. The results are incredible. The old way was basically just picking the satellites with the strongest signal, but using this new, smarter FCSD method, it cuts the positioning error by more than 45%. That is a massive improvement. And the best part? It's not because of new, expensive hardware. It's just a smarter way of thinking.
So, okay, let's recap. We started with getting satellites to fly in perfect formation. Then we solved the problem of picking the best ones out of a huge crowd. So what's next? What does all this smart technology get us? Well, it sets the stage for the next giant leap, a real, live, interconnected network that exists entirely in space. This new paradigm has a name, MCSS, or Mega Constellation Services in Space. And the idea is a game changer. You know all those constellations like Starlink that were built to send internet down to Earth? Well, it turns out they can also provide services sideways and upwards to other things already in orbit. This means satellites are about to get new jobs. Some of them will become users, kind of like your phone, just looking for a signal to send and receive data. But others will become base stations. They'll be the cell towers of space, taking a signal from the mega constellation and beaming it down to other satellites below them. And what this new architecture allows for is just mind-blowing. We're talking about moving terabits of data around in orbit every single day. The lag time, the latency, used to be hours, waiting for a satellite to pass over a ground station. Now, we're talking minutes. It means 24/7, always-on internet in space. Every satellite becomes a living, breathing part of a giant internet in the sky. So, there you have it. We went from the challenge of precision control to the challenge of smart selection. And by solving both, we're now able to build a brand new type of infrastructure in orbit, which leaves us with one massive question to think about. As we're building this incredible network in the sky, are we actually creating the next internet, or are we just building the next great cosmic traffic jam?